Welcome to a lesson with Dr. Powell. Let's take another look at inverse functions. Suppose that we have something like this. F of x is equal to x squared, where x is greater than 0 or equal to. We could take a look at this right here and realize that the graph of this looks like this. And perhaps we want to find the inverse of this function. So what we can do is swap our x's and y's. So think of this as y is equal to x squared. We swap x is equal to y squared, and we solve for y. We get y is equal to the square root of x. So if we were to draw y is equal to the square root of x, we get something like this. So we could say this is f of x up here, and this over here is f inverse of x. F inverse of x, which just means the inverse function and does what the other one does. And notice that it was exactly what we expected, squaring versus square rooting. Also notice something else. We swapped all our x's and y's. Let's draw a line where all the x's and y's are the same. Notice that swapping your x's and y's is the same thing as reflecting across the line where y is the same as x. So we can naturally just kind of get a picture. In fact, if we were to draw a function, we could naturally just draw its inverse function like this. Another thing to notice is that so x's and y's switch places, but also domains and ranges will swap places too naturally. Let's look at an example where that might become important. Suppose that we had something like f of x is equal to square root of x plus 4 minus 5. Okay, let's find the inverse function, but before we do that, let's determine what the domain and range is of this guy right here via a transformation or transformations. We know that this function is obtained from square root of x by shifting 4 units to the left. So starts over here, but then we're also shifting down 5. So the graph is something like this, roughly. You get some, and from that, let's see what we can do. We know that the domain then starts at -4 and goes off to infinity, and the range starts at 5 and goes off to infinity. So we got domain and range. Okay, let's use this idea now as we go on and actually find the inverse function by swapping your x's and y's. Keeping in mind that since this is the range of the original function, when we swap our x's and y's, this range is now going to become the new domain of our inverse function. Why is that going to be useful? Well, we'll see. Let's get going. So we have y is equal to square root of x plus 4 minus 5. Okay, now let's swap our x's and y's. And solve for y. So we get x plus 5 is equal to the square root of y plus 4. Square both sides. X plus 5 squared, and is equal to y plus 4. But then when we subtract 4, we get y equals, and we'll get a formula for f inverse of x. It'll be x plus 5 quantity squared minus 4. Now, if I were to just write this down, the domain would be everything. But we already discovered that the domain shouldn't be everything right here because domain and range is swap. This should be the domain, and so we'll need to put a comma down and put x is greater than or equal to 5. We have just found the inverse function. Now, the domain is a very important part of a function. You change the domain, you've changed the function because you've changed the graph. And the graph really is a picture of the function. So this right here is a key element when we found our inverse function, because we want the domain and range exactly to swap places here for inputs and outputs to swap. In fact, if we were to draw this, let's just see what this looks like. So we go 5 units to the left, and we go 4 units down. So 5 units to 11 points. Okay, so it's like we're reflecting across this line, y equals x, up to here. And then we graph this parabola going upward like this. Notice how it reflects. It's kind of like you have this down here and this up here reflecting. Now, we wouldn't want to keep going because this part right here is not part of the reflection of this graph at all. So we wouldn't want to have that in there. So we have just been successful at finding the inverse function to this function right here. Now, let's just consider just briefly, if we have a quadratic function and we want to find the inverse of it, if we use this technique of y equals x and reflecting it about it, swapping our x's and y's, we'd obtain something that looks roughly like this on its side. But notice there's a problem, because finding the inverse function means swapping your x's and y's and getting this. What do you notice about this? It's not a function. It does not pass the vertical line test. So, therefore, we could say that this function, as is with the full domain, doesn't have an inverse. We have to restrict it down so that the reflection passes the vertical line test and is a function. Now we can say the restriction has an inverse, and that's what it is. So that's a little illustration of why we need to be able to do this. When we need to be able to restrict things a little bit when we're finding inverse functions. And functions only have inverses when you reflect it about this line, we actually get a function. So if we reflect it and we don't get a function, then it doesn't have an inverse. Can we actually see that without reflecting? We sure can. We just swap the idea of x and y when we're thinking about vertical line test. So now we're thinking horizontal line test. So does this function pass the horizontal line test? No. If it doesn't pass the horizontal line test, it does not have an inverse. Another way of saying a function has an inverse is saying that it is 1, 2, 1, meaning one x value for every y and vice versa. So it passes both tests, the horizontal line test and the vertical line test. Then it's both a function and it has an inverse. Thanks for watching.